Hi, Kim 107 students. This is our last video for chapter 2. It'll be kind of a long one, so bear with me, but we're almost done with this second chapter. So we've talked about the chemistry we need to learn in chapter 2. Let's go back to our story about ozone, and it's important to us because it protects us from UV rays that cause skin cancer, but there's that hole over Antarctica. And the ozone layer above us has been getting thinner, which is concerning because it causes skin cancer and those rates are going up. Plus, it can cause damage to fish eggs, and that can affect the whole food chain where we have water and where we fish. So let's look at this graph. It shows us from about 1980 to 2005 how the ozone concentration has been going down. So overall, it kind of goes up and down, but overall, we've definitely gone down in the last 30 years. So we're concerned about this. Here's some satellite photos showing the hole, which is a purple color. Green is ozone, purple is lack of ozone. We can see in 1981, things weren't too bad, but by 87, we started to have a hole. By 93, it's bigger, and by 99, it's the biggest yet, and it's just getting worse. So the ozone hole was getting worse in the 90s and in the early 2000s. So what is destroying the ozone? Why is it decreasing? Is it a natural phenomenon, or is it something that humankind is doing? Well, the ozone hole is increasing in size since the early 1980s to present day. What is causing this destruction above Antarctica? Well, so scientists all over the world had a problem to solve, and they studied it, and they sent up balloons and measured ozone layers and measured concentrations of the different gases. And finally, they were able to determine that CFC molecules up in the air are killing the ozone molecules in the ozone layer. So what are CFCs? And you need to remember CFCs. CFCs stand for chlorofluorocarbons. So chloro is for chlorine, fluoro is for fluorine, and carbon's for carbon. So molecules that have CF and Cl atoms in them. What kind of molecules are those? Well, you may be familiar with these old-fashioned terms: Freon. Freon 11 and Freon 12. We don't use Freon anymore, but we used to. Have you heard that word Freon? Do you know what it's for? Where did we use Freon? Yeah, in air conditioners, right? And in refrigerators. Okay, but mostly air conditioners. Old air conditioners used to use Freon, both in your cars and at your homes and in buildings. Okay, Freon. Anyway, the scientists who figured this out won the Nobel Prize in chemistry because that was a big puzzle to everyone. So they got the Nobel Prize in chemistry in 1995. So how do CFCs, chlorofluorocarbons, kill the ozone layer? Well, up in the atmosphere where it's cold, the chlorine atoms will pop off the CFC and be a radical. The radical chlorine then can attack the ozone. And not only that, it can kill this ozone and then kill this ozone and then kill this ozone, and it can kill up to 100,000 ozone molecules before it's finally done with its murder mission. So a chlorine radical can do a lot of damage. So the equation, which you don't have to remember, is basically Cl dot, that's the radical, plus ozone makes ClO dot plus O2. And then ClO dot breaks down into Cl dot and O, and then the Cl dot can go and do it again and kill another ozone. And so again, one chlorine radical can kill up to 100,000 ozone molecules. Not good. So CFCs look like this here, these little Lewis dot structures, or models, if you will. Carbon's in the middle with the black. Chlorine is the green atom. Fluorine is the blue atom. So we have Freon 11 has 3 chlorines and 1 fluorine bonded to a carbon in the middle. And then Freon 12 has 2 of each, 2 chlorines and 2 fluorines bonded to carbon in the middle. So that's kind of what it looks like. Now, what shape are these? What shape are these molecules? Can you look at your shapes table? We have 4 atoms bonded to a center atom. What is that? Yeah, it's tetrahedral. These are tetrahedral shapes. So they're really not flat. Remember, we talked about that. They're really 3-dimensional, but it's hard to represent that on a flat piece of paper. So they're tetrahedral in shape with a bond angle of 109.5. Yeah. So, do they follow the octet rule? Well, carbon does because it has 4 single bonds around it. 4 single bonds. Now, what's not shown in that picture is that all of the chlorine and fluorines have 3 lone pairs each. 3 lone pairs each. Yeah, so we have a lot of lone pairs. We have single bonds. We have carbons in the middle, and they're tetrahedral. So why is the hole above Antarctica? We don't have any refrigerators in Antarctica. So you would think the hole would be above like Phoenix, where we have a lot of air conditioners. Well, air patterns up high carry the CFC molecules south. At that level in the stratosphere, things tend to blow south. The South Pole is the coldest spot on Earth, and we have polar clouds there that have little ice crystals in them. We need the little ice crystals to make the chlorine radicals. So reactions occur on the ice surface in those clouds to create the chlorine radicals during sunny winter days. And then the chlorine radical can start its murder mission and kill all those ozone molecules. So more UVB rays get through the hole, which is why southern Chile and Australia have much higher rates of skin cancer, because those are the most southern populated areas. Remember, in Australia, 2 out of 3 people will get skin cancer. So that's why it's south, because we need the cold clouds to have the chlorine radical pop off. But it is affecting the layer around the Earth. It's slowly getting smaller everywhere, but we got a hole above Antarctica. So resistance is futile. This is a bummer to industry because chlorofluorocarbons go in everything that uses air conditioning or refrigerators. They're cheap, they're plentiful, they work really well, they're odorless so they don't stink, they're not toxic in case there's a leak, they're not flammable if there's a fire. Industry doesn't want to stop making them. Okay, they don't really care about the ozone hole. They just want to keep their jobs and keep building CFCs. So we got a problem. We need the ozone layer to protect us from skin cancer, but these people want to keep making CFCs so that they'll have a job. So the world had to come together and retool. This is a great example of global action and worldwide cooperation. In 1978, North America banned CFCs in spray cans, like spray paint. The United Nations adopted a plan in 1977. In 1987, the Montreal Protocol was written. It's a plan to phase out all the CFCs by 2000. It's signed by 189 countries now. Even asthma inhalers had CFCs in them, and they changed in 2008. Little bitty asthma inhalers had to change. It's going to take to mid-century or a little bit later to reach 1980 ozone levels, but we are now on track for the ozone hole to start to decrease. So China is the leader in illegal CFC trade. It's second only to their illegal drug trade. I can't imagine people on street corners, hey, you want to buy some CFCs? But apparently that's a deal over in China. So the world came together. We made it illegal to make the CFCs, and companies that made them retooled. They had to research and find something to replace CFCs, and they did, and they sell it now, and they got to switch over and change their industry and update and modernize, and progress was made. So it can happen. Okay, you don't have to just lose your job. Retool, retrain, plan, and progress can move you ahead. So as we can see in this graph, the ozone hole takes a big dip around 2000. Look at where we are in 2017. The hole's pretty deep, but it's projected from 2020 on that the ozone's going to increase and recover. It'll take us until about 2065 to get back to the 1980 levels. All right. Here's another graph. Sorry about the dog. Here's another graph showing how, hush, Jolie, hush. How in pink we have our CFCs and how they go down dramatically in production in the 90s and the 2000s. So why do we still have an ozone hole today? Well, again, remember, these CFC chemicals persist in the atmosphere for 100 years. Although we're no longer producing CFCs, they're still up there in the air from when we let them out 20 years ago. It's going to take around 2050 to 2070 for the ozone layer to recover to 1980 levels. So what are we replacing them with? Well, scientists studied and determined some good replacements. We have like a middle replacement and the ultimate replacement. The middle replacement is HCFCs. H is for what element? What element is H? Hydrogen, right? So we're going to take a chlorine off and put a hydrogen in its place. These can be used until 2030. So again, we take a chlorine off and put a hydrogen on. They still may have a chlorine atom, but at least it's not as many as it had. So again, that's why this is a middle replacement. Ultimately, we have to switch to HFCs. The chlorines are gone, replaced by hydrogens. So again, the ultimate replacement is to remove all the chlorines and replace them with hydrogen. So hydrogen hydrofluorocarbons are what's being phased in now. No chlorine atoms at all. So example would be CH2F2 and C2HF5. They're often blended together, non-toxic, non-flammable. The freon now is called R410A. Your new air conditioners being built now use this as their replacement. They don't use freon anymore. So anything built really in the last 10 years probably doesn't use freon anymore. We're doing a good job switching over. So if you look at this great graph, the CFCs are green and orange. Look at 1990. The whole circle is practically green and orange. Then we start switching to the middle replacement, which is blue and yellow. So 1995, we've already done a good switch to the blue. 2000, we got a lot of blue and yellow, and then we got a lot of purple. Purple's the ultimate replacement, the hydrofluorocarbons, HFCs. So even by 2000, we're probably halfway there, and by 2006, we're almost all the way there. So it's possible. We can do this. We can switch. We can change. We can retool. We can solve environmental problems. So problem solved. So the world came together with science, solved a critical environmental problem. Laws were successful in making a change for the betterment of humanity. And here's a picture of a hydrofluorocarbon. Here, hydrogen's in white, fluorine is green, and carbon is black. Anyway, that's it for chapter 2. We finally finished. Sorry about the dog. Catch you later, Team 107. Bye-bye.